Hi students, in this video we're going to go over section 410, the element method of proof and counterexample. So we're revisiting proofs again. So in this section we're going to discuss the element method of proof. We're going to prove that one set is a subset of another. We're going to prove equality of sets. We're going to prove set identities, and we're going to discuss counterexamples. So before we go into some of the examples, some of the proofs that I'll do in the slides, I'm just going to go over some information first. So first we're going to start with going over discussing the method of generalizing from the generic particular. And we had mentioned this in the previous chapter, chapter 3, when we were doing proofs. So to show that every element of a set satisfies a certain property, we're going to suppose that X is a particular yet arbitrarily chosen element of the set. And then we're going to show that X satisfies that property. Direct proof. A direct proof starts with a premise, a hypothesis, and then proceeds directly to the conclusion with a sequence of statements which are either givens or deductions from previous statements, and whose last statement is the conclusion to be proven. Proofs involving sets. So we can use the method of direct proof, something we talked about in the previous chapter, to establish a subset relationship. Such a proof is called the element method, or sometimes called element argument, and it is a fundamental proof technique of set theory. So the element method of proof. So if we are proving that one set is a subset of another, we're going to let set A and set B be given, and then to prove that A is a subset of B, you're going to suppose X is a particular but arbitrarily chosen element of set A, and then you're going to show that X is an element of B. So that's what we'll do if we're just showing that one set is a subset of another. Equality is going to be a little different though. So equal sets, we had a definition for this in a previous section earlier in the chapter, and we're just revisiting it here. But set A equals set B, written this way, if and only if every element of A is in B and every element of B is in A. So symbolically, if A and B are equal to each other, if those sets are equal, then A is a subset of B and B is a subset of A. So this is going to impact how we do the proofs for equal sets. So this is our element method of proof when we're proving two sets are equal. We're going to let set A and set B be given, and then to prove that A is equal to B, you're going to have two parts. The first part will be to show that A is a subset of B. So you're going to suppose that X is a particular but arbitrarily chosen element of A, and then you're going to show that X is an element of B. And then part 2, you're going to do the other subset. You're going to prove that B is a subset of A. To do this, you're going to suppose that X is a particular but arbitrarily chosen element of B, and then you're going to show that X is also an element of A. There's going to be two parts to your proof when you're proving equal sets. Here are some procedural versions of set definitions we've gone over previously. So we're going to let A and B be subsets. We're going to let U be the universal set. And we're going to suppose that X and Y are elements of your universal set. So the first one here, if X is an element of A union B, that means that X is in A or X is in B. Remember, union, we interpret that as or we interpret as union. And then the second one says that X is an element of A intersection B. That means that X has to be an element of A and has to be an element of B. Remember, when we see the word and, we think of that as intersection. And vice versa. And then 3, if X is an element in the set difference between A and B, that means that X is in A and X is not in B. You may remember when we went over set identities that the set difference is equal to A intersection B complement. And then 4, X is an element of A complement. So complement, we interpret that as not. So that means that X is not an element of set A. These are going to help us with our proofs. And here's a theorem for thumb. subset relations. So for all sets A, B, and C, we have the inclusion of intersection. So A intersection B is a subset of A, and A intersection B is also a subset of B. Let's bring back our Venn diagrams for a minute so we can visualize what's happening here. Here's our universal set. Here we have set A. Here we have B. Here we have their intersection. So let's just we'll look at this one here. So there's your intersection, A intersection B. That's clearly a subset of B, right? And you could do the same, think it out the same way with the other one. And then inclusion of union. A is a subset of A union B, and B is a subset of A union B. Let's do a Venn diagram for this one as well. Here's your universal set, there's set A, there's set B. So if this is A here, that is obviously a subset of this whole region here, all of that. And you could think of this one in a similar way too, right? If this is your B, set B, that's obviously inside of A union B. It's a subset of A union B. And then you have transitive property of subsets. So if A is a subset of B and B is a subset of C, then A is a subset of C. Let's visualize this one too with a Venn diagram. So A here is a subset of B. So I'm going to draw A entirely inside of B, but B is a subset of C. So I'm going to put B inside of a circle representing set C. So A here inside of B, and B is inside of C. So then A is also inside of C. So if A is a subset of B and B is a subset of C, then A has to automatically be a subset of C. All right, example 1, we're ready to start doing some proofs now. So for all sets A and B, we want to prove the following, that A is a subset of A union B. Let's just go back here. So this is what we're proving. We're proving the inclusion of union. So you're going to start by writing proof, and then we have sets A and B, so let's let A and B be any sets, right? Because it's supposed to work for all sets. So we'll let A and B be any sets. And then we're going to suppose X here is an element of A. So we have X, which is a particular yet arbitrarily chosen element of set A. Then X is in A, or X is in B. This is a generalization here. Think back to one of our first chapters where we went over logic and we talked about the disjunction, the or, P or Q. Just one of those had to be true for the whole disjunction to be true. So if X is in A, then we can say that X is in A or X is in B. And it's still a true statement. Then X is an element of A union B, because we're rewriting or as the union. We'll say by definition of union. Therefore, we need a concluding sentence now. Therefore, A is a subset of A union B, because we showed that X started out as an element in A, and then through a generalization and through a definition, we showed that that same X was also an element of A union B. So we showed the subset relationship. And then let's just go finish that up with a little QED to conclude the proof, to show the proof is over. Example 2, for all sets A, B, and C, prove the following. The set difference between A and B intersected with the set difference between C and B is equal to the intersection of A and C and the difference of that with B. This is an equality. We're showing that this set is equal to this set, right? So you're going to have, this is going to be a longer proof because we're going to have two parts to this proof. But we're going to start out, you're going to put proof down. We're going to let A, B, and C be any sets. And then part 1, this is, we're going to prove, what are we doing in part 1? Let's explain it. We're going to prove that the set difference of A and B intersected with the set difference of C and B is a subset of the intersection between A and C and the difference of that with B. So we're showing the subset in one direction for part 1, and then we'll have a part 2 where we show the subset in the other direction, right? So there's going to be 2 parts for when you're proving equality. So we're going to suppose X is an element of this set here. Copy that down. Okay, so we have an element in that first set, and we're going to show that that element is also in this part over here through a series of steps. Okay, by definition of intersection, because of this intersection right here, X is an element of the set difference A and B, and X is an element of the set difference between C and B, right? So we're just rewriting the intersection with the word and. I'm going to go on to the next slide so I have more room, and now we're down to the set difference. So we're going to use the definition of set difference in the next step. So let me just scroll up for a second. So we're making a lot of use of these here in our proofs, okay? Okay, so I'm going to write by definition of set difference, X is an element of A, and X is not an element of B. Okay, that's for the first one. That's just this part here. We still have our word and, so I'm going to copy that down, and then we're going to use the definition for set difference for this other part. And X is an element of C, and X is not an element of B. Okay, well now you have this repeated, so we can condense this. So X is an element of A, and X is an element of C, and X is not an element of B. Now, so we broke it down. We went from having the symbols for intersection and set difference. We broke it down with the words. Now we're going to build it back up. So this and is going to become the intersection again. So by definition of intersection, X is an element of A intersection C, and we still have this and in this part, so copy that down, and X is not an element of B. Okay, we're still putting it back into set notation, so then we're going to say by definition of set difference, X is an element of A intersection C, and the difference of that was set B. So we went from an element in here, we broke it down and we built it back up. So we went from here to here. So we showed that that element of X, it was in this set, but it was also in this set, showing the subset relationship. So I'm going to put down one more sentence to finish up part 1. So we're going to say, therefore, this set is a subset of this set. Okay, that's just part 1. Now we're going to kind of repeat the process, but for the subset in the other direction. So we're going to say part 2. And we are going to prove that A intersection C, set difference of that was B, is a subset of A, set difference A and B intersected with the set difference between B and C. Okay, so we're going to suppose X is an element in this first set here, and we're going to show through a series of steps that it's also going to be in this set over here. So suppose X is in there, and we're going to break it down with the definition. So by definition of, which definition do you think we're going to be using? Set difference. So by definition of set difference, X is an element of A intersection C, and X is not an element of B. Now we're going to break down the intersection. So by definition of intersection, X is an element of A, and X is an element of C. And you still have this part, so copy that down. And X is an element of B, or not an element of B. So I'm just going to kind of do a little rearranging here. This is going to be generalizing. So I'm going to say X is an element of A, and X is not an element of B. And X is an element of C, and X is not an element of B. And we're going to build it back up. So we broke it down. We're going to build it back up into our set notation. So then by definition of set difference, X is an element of the set difference between A and B. So we're just rewriting this part. And we still have this and here. And then use the set difference on this. X is an element of the set difference between C and B. When you're doing these, when you write down by definition of intersection, by definition of set difference, etc., you're doing those individually. So do not combine definitions. Do not combine and say something like by definition of intersection and set difference, and do multiple things in one step. Do not do that. So don't condense this any more than it already is. So we want it to be clearly, we want this so that anybody reading it can clearly follow. So just do one definition at a time. Even though it looks like a lot of writing, it will be. These are going to be the most extensive proofs that you do in this class. But if you are omitting anything that we have in here, most likely on the tests, quizzes, or whatever, you're going to lose points. So don't take out any of the work that I'm putting in here. If you omit things, try to combine things, you will lose points on a test. So make sure all of these steps are included and written down. Okay. Now what are we going to do? Now we're going to take care of this and. So by definition of intersection, we're going to have that X is an element of the set difference with A and B, intersected with the set difference between C and B. Okay, I'm going to go on to the next slide. I need one more line for this part 2. So this whole part 2 was to show that if you had an element in this set here, it's also going to be an element in this other set, showing the subset relationship, which we did. So we're going to say, therefore, this set here, the one that we started with, is a subset of the set we just ended with. Okay, now we're going to conclude the overall proof. So I'm going to say, since set difference between A and B intersected with the set difference between C and B is a subset of A intersected with C, the set difference of that with B, and A intersected with C, the set difference of that with B, is a subset of the set difference between A and B intersected with the set difference between C and B. So since we have the subset in both directions, then these two things are going to equal each other. So I'm going to say set difference between A and B intersected with the set difference between C and B is equal to A intersected with C and the set difference of that with B. And actually we should put down by definition of set equality. And then we're finally done, so we'll put our QED at the end. So these are going to be longer proofs, just in general. So again, don't try to skip steps. Shortcuts are going to make long delays. So if you end up skipping things, you're going to end up losing points in the long run. So if you don't take out anything that you see on these proofs. All right, example 3. So for all sets A and B, we want to prove the following. And this we've seen before. This is actually De Morgan's laws for sets. So we are proving one of De Morgan's laws for sets. So since it's equality, we're going to have the two parts to the proof again. All right, I'm just going to start on the next slide. We're going to write proof. We're going to let A and B be any sets, right? This is going to has to work for all sets. So A and B are any sets. And then we're going to start with part 1, which is going to be the proof that this part is a subset of this part here. So we're going to prove that A intersected with B, and the complement of that is a subset of A complement union B complement. So we're going to suppose X is an element of that first set, A intersection B, the complement of that. And then we're going to break it down and build it back up. So we're just going to use our definitions. So by definition of complement, X is not in A intersection B. Okay, this means that it is false that X is in A and X is in B. So by De Morgan's laws of logic, back from that earlier chapter, this implies that X is not in A or X is not in B. So by definition of complement, X is in A complement or X is in B complement. Okay, I need one more line for this part 1, but I've run out of room, so we're going to go to the next page. And I'm going to say by definition of union, X is in A complement union B complement, because we had an or here. Okay, that's part 1. Now we're going to do part 2. And here we're going to prove that A complement union B complement is a subset of A intersection B, the complement of that. So we're going to suppose X is an element of A complement union B complement. By definition of union, X is an element of A complement, or X is an element of B complement. By definition of complement, X is not in A, or X is not in B. This means that X is not in A, or X is not in B. So by De Morgan's laws of logic, this, next slide, implies that it is false that X is an element of A and X is an element of B, which can be written as X is not an element of A intersection B. And this is by definition of intersection. And then by definition of complement again, this means that X is an element of A intersection B complement. Okay, now we're concluding the whole proof, so we're going to say since A intersected with B complement is a subset of A complement union B complement, and A complement union B complement is a subset of A intersection B complement, then these two things are equal. By definition of set equality. And we are done. QED. Example 4. For all sets A, B, and C, prove the following. So we have another equality, so another two-part proof. So I'm going to go on to the next slide so it's just more room. So we're going to start out by writing proof, and we're going to let A, B, and C be any sets. Okay. Part 1. We're going to do one of the subset relationships. So we're going to prove that this here is a subset of this here. All right, so we're going to pick an arbitrary but particular value from this set. So we're going to suppose X is an element in there. And then eventually we're going to show that's also in here too. All right, so by definition of union, because we're going to start to break this down, X is in this set difference, or X is in the other set difference. Okay. Now you're actually going to have, this is a little different than the previous examples we've done, the previous proofs we've done. You're actually going to break this down into two cases. The case 1 is going to be X is in this first set difference. All right, so case 1, X is in the set difference between A and B. By definition, of set difference X is in A and X is not in B. We have to break it down into cases because of this being an OR. If you look at this proof and you compare it to the one we did previously, we had an intersection here. And so that case 1, case 2 wasn't necessary because the intersection meant that your element X had to be in both of those things. Here, because X doesn't have to be in both, it just has to be one or the other, that's what gives us the cases. Okay, I'm going to continue with this. I'm going to say, but since X is in A, we have that X is in A or C by definition of union. Because if it's in A, then you can say it's in A or C. Just remember, think back to the first example we did in this video. Hence, X is in A union C, and X is not in B. And then, can I squeeze one more line in here? By definition of set difference, X is an element of A union C, set difference of that was B. So that's the end of case 1 for part 1, but now you need case 2, still in part 1. So the case 2 will be assuming this part here. Notice this is still indented. So case 2, X is an element of the set difference between C and B. Okay, so by definition of set difference, X is in C and X is not in B. But since X is in C, we have that X is in C or A, but I'll change the order here because it's commutative. So I'll say X is in A or C, the union. And I'll put by definition of union. Hence, X is in A union C, and X is not in B by definition of set difference, X is an element in A union C, and the set difference of that was B. Okay. Still in part 1. We're still doing part 1, but I'm going to come out of the indent now. So I'm going to say in both cases, X ended up being an element in A union C intersected set difference was B. So in both cases, we showed that if X is in this set, or if X is in this set, in both cases, X is in this set up here. So we've shown the subset from here to here. We've shown that subset in that direction. All right, so I'm going to finish up part 1. Finishing up part 1, I'm going to say therefore, set difference between A and B union with the set difference between C and B is a subset of A union C, the set difference of that was B. So that's the end of part 1. Then we're going to go into part 2. So part 2 is to prove that A union C, set difference of that was B, is a subset of the set difference between A and B union set difference between C and B. So now we're doing the subset in the other direction. So we're going to suppose that X is an element in that first set. By definition of set difference, X is in A union C and X is not in B. By definition of union, X is in A or X is in C, and in both cases, X is not in B. So X is in A or it's in C, but regardless, it's not going to be in B. All right, case 1, X is in A and X is not in B. Right? X is either in A or it's in C. So case 1, I'm going to say it's in A. Right? In both cases, it's not in B. By definition of set difference, X is in the set difference between A and B. And then by definition of union, X is in that set difference union another set difference, C minus B. And as long as this is a union, doesn't matter what I put over here, right? Because like we mentioned before, if we're doing a union, for this to be true, for it to be a true statement, X only needs to be in one or the other, right? Or both. And we already know that X is in the set difference between A and B. So you can put or anything else, union anything else. And the reason why we're picking out the set difference C between C and B is because this is what we're trying to get to. And that's the part I was missing. Now we're going to do case 2 in part 2. So case 2, X is in C and X is not in B. By definition of set difference, X is an element of the set difference between C and B. By definition of union, X is an element in C, and the difference between C and B, union the difference between A and B. So we're doing a similar technique as earlier, right? So this is a true statement as long as one of these is true, right? Because we have the union, one or the other or both, and we already know this part's the true part. So in both cases, X is an element of the set difference between A and B, union the set difference between C and B. Therefore, A union C, the set difference of that with B, is a subset of the difference between A and B union the difference between C and B. So that finishes up part 2. And now we want to conclude the whole proof. So we're going to say since this set here is a subset of this set, and this set is a subset of this set, then two sets are equal. By definition of set equality. And we're done, so QED. Counterexample, so disproving that two sets are equal. So counterexamples are used to disprove a statement. Remember, a universal statement says a certain property is true for all objects. And a counterexample is an example used to prove a universal statement is false. And you may remember from a previous chapter, you only have to come up with one example showing that the universal statement is false, just one instance where it's not true. So for example 5, we're going to use a counterexample to disprove the following. So the following says that the set difference between A and C is equal to the set difference between A and B intersected with the set difference between A and C for all sets A, B, and C, right? So this is written like it's a universal statement, but we're going to show that this is actually false. So instead of proof, we're going to write counterexample, and we're going to pick out particular sets for our counterexample. So I'm going to say let A be equal to the set containing 1 and 2. B can be the set containing 1, and C is going to be the set containing the number 2. Then the set difference between A and C, this part here, would be the set containing just the number 1. Just if you're looking at these and doing the set difference, you just get 1 as your element in the set. And now let's look at this part here. If we have set difference between A and B intersected with the set difference between A and C, this would be equal to this part here is, what is this part here? The set difference between A and B would be 2. Looking at these sets here. Still doing the intersection, so I'll keep that symbol. And then this we just found that was the set containing the number 1. But now if we do this intersection, that's going to give us the empty set. So since this set here containing the element 1 is not equal to the empty set, then the set difference between A and C is not equal to the set difference between A and B intersected with the set difference between A and C for all sets A, B, and C. You could just end with a little QED or something. And it is possible that you could come up with sets A, B, and C so that these actually end up being true. But remember, this is written like it's a universal statement, and we're showing that it's not always true. So we're disproving that universal statement with a counterexample. So you want to make sure that when you come up with a counterexample, you're disproving the universal statement. Well, that's it for this section. Have some fun with the homework, and I'll see you in the next video.